Okay, welcome back everyone. In this very important video, we're going to be proving the ideal gas law using only the basic laws of physics. So this video may be a little bit longer than some of the others, but the derivation is really important because it really ties together what we're talking about in physics with what you've already learned of the ideal gas law. So because this is the quote ideal gas law, that means that there are some things that we assume. So we're going to make 4 assumptions. First of all, we're going to assume that all the molecules in our gas have the same mass, and we'll call that m, and we're going to say that this mass is small enough to neglect gravity. In other words, gravity is not going to be exerting enough force on these particles to be of concern to us. And they are in random, constant motion. So that's our first assumption. Our second assumption is that the gas molecules are relatively far apart and they occupy a large volume compared to their separation. So what this really does is it sets up the groundwork for our derivation, and it says that we have a gas which is a low pressure gas. Because if you have a highly compressed gas, then there are other forces that come into play which make this derivation completely wrong. Okay. The third one is that the only forces between molecules occur during collisions. And what this means is that we can neglect gravity, we can neglect, so no intermolecular forces. Okay, so no forces between one molecule and its neighbor. The only thing is when they collide. Okay, and then finally, we're going to assume that collisions are perfectly elastic. And you might remember from the momentum unit, this means that there's no change in kinetic energy. Okay, so these are our assumptions, and we're going to pretend like we're dealing with some box with sides L. Okay? And we're going to start with force. Alright? Good place to begin. We can define a force as equal to mass times acceleration, but the way that Isaac Newton wrote it was a change in momentum over a change in time. And so what this is the force exerted by one gas molecule collision on the wall of the container. And so if I think about, here's one wall of the container and here's the other wall somewhere over here. So there's a molecule which comes in with a speed Vx initial. It strikes and rebounds perfectly elastically, and ends up with Vx final. And because it's perfectly elastic, we can say that Vx final is equal to negative Vx initial. And furthermore, we can say that the force is equal to the change in the momentum, which is mass times velocity, divided by the change in time. And so this is going to be the final momentum, so mvx final, minus the initial momentum, and let's say for fun that to the left is positive, so then I'm going to have a negative Vx, a negative mvx initial. And as a matter of fact, what I can do is rewrite this and just say that I have basically two speeds. I have negative Vx and I have positive Vx. So that means that my change of momentum is really mvx minus negative mvx. So I'm making use of this fact here, that they're equal but opposite. And I'm dividing by time. And we've seen this before, that when things bounce, that you simply have to double the momentum and divide by the change in time. Okay, now we're going to assume that in between collisions with the wall, we'll say that in between successive collisions with the wall, the molecule is going to travel the entire length, L, in a time t. Now how much time is it going to take? Well, it's traveling a distance of L, and it's traveling with the speed of Vx, so t is equal to distance over speed. Remember that speed is distance over time. And the return trip also takes t equals L over Vx. So one complete sort of back and forth. So making one full circuit of this back and forth motion is going to take twice that, so we can write delta t is equal to 2L over Vx. So from this we can conclude that the number of collisions, and this is very important, per unit time that a molecule makes, just one molecule, with a wall is Vx over 2L. Now if you want to see how I got that, I could say that the time per collision is equal to 2L over Vx. So that means that the collisions per unit time is Vx over 2L. So now I take this and substitute this back for my force equation, and I know that 1 over delta t is basically Vx over 2L. I take that and plug that back into here, and what I'm going to get for my force is F is equal to 2mvx divided by 2L over Vx. So the 2's will cancel out, and I'm going to get mvx squared over L. And at this point I want to point out that we have a Vx squared, and hopefully that, oh, we have an mvx squared, so hopefully that reminds you of something. Okay, now we know that the random motions of many particles produces a relatively constant force. And the pressure that results from this is the total force over the area. Okay, so the force is all of those added up, and then L squared is the area of one of the sides. So remember that the force is mv squared over L. Okay, so I'm going to get L cubed in my denominator if I multiply 1 over L squared by all the forces, and I'm going to have mass times v1x squared plus v2x squared plus v3x squared, so on and so on. And all these different terms are the different molecules hitting the wall. They happen to be pretty much the same number. But just in case they're not, let's take an average. Okay, so we're going to take Vx squared bar, and so what this means is average. Okay, so literally what we're calculating is the average of the squares of the speeds. Okay, and so that's basically v1x squared plus v2x squared plus v3x squared dot 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 dot, all divided by n, the number of molecules. Okay, so now what we can do is we can replace this m v1x squared, etc., with the quantity n times vx squared average. So that's if I multiply each side of this equation by n, the number of molecules. So the pressure becomes, I still have an m, and I have an n, and then I'll put my vx squared average right here and divide that by L. Okay, so I could write that as L cubed, sorry. So that's n m vx squared average over L cubed. Okay, and there's a couple things to notice. First of all, L cubed is equal to the volume, which is just V. So the pressure is now equal to n m vx squared average over V, capital V for volume. Okay, and if I multiply each side of this equation by volume, I get PV equals nm vx squared average. So what I've done, I'm not completely done, but what I've done so far is I've shown that pressure and volume are inversely related. And we saw this in our lab, where the right way to graph it was 1 over volume to get a straight line. Okay, so that's what this implies. So we already have some great information about what's going on in the lab. Okay, now let's deal with this stuff on the right side. One thing that we know is that these collisions don't just happen if I scroll up. They don't just happen with the left and the right sides of the box. They happen with the back and the front and the top and the bottom, so they happen with equal frequency. Okay? So the collisions occur with equal frequency on any of the 3 axes. So what that tells us is that Vx squared average should be equal to Vy squared average, and that should be equal to Vz squared average. The average speeds of the molecules should be about the same. Okay? And a modified Pythagorean theorem tells us that the average speed, so think about this as a triangle, okay, that doesn't just have x and y but also z. This is kind of an expanded Pythagorean theorem. It's like finding the diagonal of a cube in some ways. It's Vx squared average plus Vy squared average plus Vz squared average. And that's equal to 3 times Vx squared average. And so what this means is that Vx squared average is equal to 1/3 V squared average. Okay, now let's actually give this V squared average a name. Well, let's do something to it first. Let's take the square root of it. This is what we call VRMS, and if you go on in physics you'll see this again, but this is called the root mean square speed. So the root makes sense because we're taking a square root. The mean is because of the average, and the square is because we've squared the speed. Okay, so it's the square root of the average speed squared of the molecules in a gas, and it's actually a very important measure of a gas. Okay, now we're going to rewrite what we had before. We had PV equals NMVX squared average, but now we can write this as PV equals 1/3 NMVRMS squared. Okay, so this is a fancy way of removing V average. Okay? Alright, now this next part you're going to have to believe me. Okay? I'm going to claim that the average kinetic energy for a particle moving in one dimension, a bunch of particles moving in one dimension is, okay, and you're going to have to trust me, 1/2 mvx squared is equal to kT over 2, where T is the temperature and K is the so-called Boltzmann constant. And it has the value of 1.38 times 10 to the negative 23rd joules per Kelvin. Okay, so you're just going to have to believe me. Now, I'll put a little asterisk here. If you don't believe me, then what you have to do to prove this is to solve the following. That Vx squared average is some weird square root m over 2 pi kt times the integral from negative infinity to infinity of Vx e to the negative m v squared x over 2kt with respect to Vx, which is equal to kt over m. So I give you the choice. You can either try to solve this or you can just believe me for now. Okay, so that's what it is in one dimension, that you get a factor of kt over 2. So in 3 dimensions, it's just 3 times as much. So the kinetic energy in 3 dimensions is 1/2 mv squared, which is equal to 3/2 kt. And this is how we bring temperature into the mix. Okay, so since kinetic energy is equal to 3/2 kt, and since we have pressure times volume is 1/3 nmv squared, okay, we could say that PV is equal to 1/3 times n times 1/2 mv squared times 2, which is equal to 2/3 n times kinetic energy. So I'm going to pause for a second because that step is a little bit tricky. I want to make sure that you're okay with it. Okay, And so what we get as a result of this is that PV is equal to 2/3 N times 3/2 KT, and this leads directly to the microscopic ideal gas law. PV equals NKT. N is the number of molecules, K is the constant, and T is temperature. Okay. So there we go. Bam. So now let's actually write this in terms of what we know with the gas constant R. So sometimes the number of molecules is equal to the number of moles times Avogadro's constant. So this is 6.02 times 10 to the 23rd molecules. Okay, now something interesting for you to try is to whip out your calculator and do Avogadro's constant times Boltzmann's constant, and guess what you're going to get when you do Na times K. I'm going to pause and wait for you to do that. Okay, that's right, you get 8.31 joules per mole Kelvin. In other words, Avogadro's number times Boltzmann's constant is R, the ideal gas constant. So that means that pressure times volume is equal to the number of moles times Avogadro's number times K times T, and we've just shown that this is equal to R, and therefore we have proved the ideal gas law. And that's all I got. See you next time.